Good morning, everyone. This is Hyunwook Park from KAIST. Today, I will share our research about machine learning-based power integrity design method, especially focusing on decoupling capacitor design. The title is Polish Gradient Reinforcement Learning-based Optimal Decoupling Capacitor Design Method for 2.5D and 3D ICs using Transformer Network. Here's my contents. First, introduction, and I will propose Polish Gradient RL-based optimal decap design method using Transformer Network. Next, verification is followed, and finally I will conclude my presentation. Recently, machine learning approaches have been started to introduce in hardware layout design. Our TAREP also proposed our Design by AI research project, ADA in short, for 100% design automation for hardware layout, especially focusing on this HBM module. These approaches can be classified by the type of machine learning. First, in the case of supervised learning, we can use it for fast and accurate prediction during design flows. Especially in our fields, it can be used for SIPI performance evaluation. Next, unsupervised learning can be used for tests during design flows. And the final one is reinforcement learning, since it can drive out optimal action sequence called policy. It focuses on decision making during design flows. In our fields, SIPI optimal design. And we will focus on the reinforcement learning for this presentation. And these are the reasons why we choose reinforcement learning for optimal layout design considering SIPI. There are four main advantages compared to conventional methods. The first one is that performance of RL-based method improves with time as more previous layout design patterns and corresponding SIPI performance are accumulated in the database. The second one is accurate design. Since it is based on the massive data-driven knowledge, it can drive accurate results while excluding heavy dependency on SIPI engineers' empirical knowledge. Also, it can provide fast optimization thanks to its own action selection strategies to reduce search space. Moreover, due to nowadays modern computing power such as GPUs and multi-core CPUs and development of advanced RL and machine learning algorithms, it can achieve fast optimization. The last advantage is that RL can give us reusable, scalable, and flexible solution. RL is not a ground optimization method of a particular design such as genetic algorithm and Bayesian optimization, but provides a general solution model itself. Let me briefly introduce RL for layout design considering SIPI. Actually, RL is the algorithm that solves the problem defined by Markov decision process, MDP parameters such as state, action, reward, and policy. The main goal of the RL is to learn the policy which determines how to act in order to maximize the reward by interaction with the environment states. And learning the policy means to optimize weights of value or policy network. The upper figure shows the schematic diagram of RL for the layout design considering SIPI. As you can see, there is an design agent, and this agent learns optimal action, which is layout design for given environment such as PDN or channel. The reward given to the agent is the evaluate SIPI performance that acts as a feedback to the agent. Below figure shows the unfolded diagram in time. After the value or policy neural net is optimized, if we choose the best action in every state starting from the initial design, then finally it reaches to the optimized design. Especially in PI fields, one of the most big issue in 2.5D and 3D ICs is simultaneous switching noise. Broadband simultaneous switching current (SSC) driven by chip I/O buffers flows into hierarchical PDN depending on their frequency range. And once the SSC components miss the high peak anti-resonances of the PDN impedance, large SSN occurs, causing logic failures. Therefore, we need to design PDN carefully to lower the PDN impedance in the broadband frequency range. As you know, decap design is one of the most important processes to lower the PDN impedance to ensure stable power supply for ICs. We usually design decaps to meet a target impedance, which is the criterion for ensuring tolerant voltage fluctuation. Therefore, we can say that optimal decap design refers to the layout of decaps satisfying the target impedance with the minimal layout area. These are the previous works of RL-based decap design methods to satisfy the target impedance. All of these are value-based RL method without or with value approximator. The first one is Q-running based onboard decap design method proposed by Kaisti in 2018. The second one is deep Q-running based onboard decap selection method proposed by MST in 2019 and 2020 with convolutional neural network as the value approximator. The last one is deep Q-running based on interposer and on-chip decap design method proposed by Kaisti in 2020 with the CNN as the value approximator. However, all of these previous value-based RL method with simple value approximator are limited in the size of action space, which is the number of decap available ports. Their coverage of such space is limited. Since the policy is totally determined by the estimate value function in the value-based RL, small change in the value function can lead to large policy jump, causing divergence when training. Especially policy-gradient methods can overcome the limitations of the size of the action space. Instead of approximation of the value function, policy-gradient methods directly parameterize the policy, which is PDFs of action for given states. The neural network that approximates PDFs is called a policy network. Then the weights of the policy network can be trained by gradient updating with the value function as a loss function. Therefore, smooth policy improvement can be performed unlike the previous work so that it can significantly enlarge the size of the action space without divergence when training. Not only the way of updating the policy network, but also one of the most dominant factors that affects the performance is the policy neural network itself. Not long ago, RNN-based sequence-to-sequence neural network models were widely used to solve combinatorial optimization problems. But in 2015, attention-based neural network called pointer network was proposed and its performance critically outperformed the previous network. This is because attention-based neural network is superior in long-term dependency since attention gives the decoder access to all the encoder's hidden states. Details on the attention mechanism is shown in the below figure. Attention mechanism is weighted message passing algorithm between nodes in a graph. The attention weight reflects relationship between all of the labeled nodes, and that of the message value V depends on the compatibility of its query Q with the key K of the neighbor. This mechanism is also called a single-head attention. With more sets of value, query, and key, parallel computation of single-head attentions is called multi-head attention. In this section, we propose a policy gradient RL-based optimal decap design method using transformer network. This is the overall concept of the proposed method. For a given input sequence, there is a set of decap available positions. A policy network outputs a decap assignment sequence. The policy network consists of an encoder and a decoder, which are the attention-based transformer network parameterized by weight zeta. And the network directly parameterizes probability distribution pi zeta of a driving output decap sequence for given decap available ports. The goal of the proposed method is to optimize the transformer network to maximize to maximize number of frequency points meeting the target impedance. And we use policy gradient updating when optimize the transformer network. Here are the details on the defined MDP parameters. First of all, state S is defined as a set of four-dimensional vector of decap available ports, which is configured of X, Y, Z coordinates and status of unit cell. Action A is driving a decap assignment sequence represented in a vector. The action A can be expressed as a permutation of sub-actions AT, which are defined as adding a unit decap at a certain position. Reward is modeled as number of frequency points satisfying the target impedance divided by the number of total frequency points. And the reward is used in loss function calculation for training the policy network. Policy pi is the encoder-decoder transformer network that parameterizes PDF of decap assignment sequence given the state. Hence, it can be factorized as PDFs of sub-actions. This is the encoder transformer network of the proposed method. The main purpose of the encoder is to embed input state into high-dimensional node embeddings H. The network consists of attention layers, which are configured of a multi-head attention layer and feed-forward layer with skip connection. Especially multi-attention layer enables to create node embeddings H by reflecting the couplings between nodes without recursive calculation. And this is the decoder transformer network that provides the decap assignment sequence A. The decoder is configured of decoding units, and each decoding unit sequentially outputs the next position AT of a unit decap every time step, where probability is maximized. The decoding unit consists of one multi-head attention and one single-head attention layer for a given input as the encoder output node embeddings H and a context node embeddings HC. Probabilities are computed through the multi-head attention and single-head attention layer. One of the most important things in the decoder is modeling the context node embedding because it becomes a query and creates a polish for the next decap by attention mechanism. Therefore, by using encoder node embeddings, context node embedding is modeled to reflect the positions of probing port, first and previous decap assignment position, and on-chip ports. Hence, the context node embedding is expressed as a concatenation of node embeddings of them. Here are the details on calculation of PDFs for selecting the next unit decap assignment position. First, in the multi-head attention layer, by multi-head attention of the defined context node embedding HC and encoder output node embeddings, a new context embedding HC prime is computed. Then in the single-head attention layer, a new query QC prime is computed by linear projection of HC prime. And with the QC prime and keys from linear projection of encoder output node embeddings, utility U for every node can be computed by scale dot product attention. And using softmax function, we can convert utilities into probabilities for decap positions. And this is the loss function or value function for training the encoder-decoder transformer network. The loss function should be designed as the evaluate performance of the assigned decaps. So we define the loss function as the expectation of a reciprocal of reward. Then updating theta of the police network to minimize the loss function means training the network to output a decap sequence that meets target impedance in more frequency points. Finally, using policy gradient algorithm reinforced with roll-out baseline, we train the policy network. By policy gradient theorem, gradient of loss function can be derived as the equation in the slide. The reason why we subtract the baseline is to reduce the variance when training. Repeating, the ultimate direction of training is to update weight theta in order to minimize loss function, which leads to satisfaction of the target impedance. For verification, we apply the proposed method to a test hierarchical PDN and compare the loss convergence characteristics with the previous value-based RM method. The test hierarchical PDN setup for this work is equal to the test PDN in our previous work, but only the number of uninterposable unit cells is increased to implement the largest action space. Also, we use the same unit cell and MIMCAM model in the previous work for fair comparison. We vary the size of action space n equals 50, 100, 150, and 200. The lower table shows the hyperparameter setup of the encoder-decoder transformer network and that of the training. The thing we want to emphasize is that we share the same hyperparameter setup for all the cases of the action space. This can potentially lead to the reusable, scalable, and flexible policy model. This is the optimized decap design result in the case of n equal to 100. A total number of 13 unit decaps of 1.3 nanofarad were assigned closer to the probing port to reduce the loop impedance. The interesting thing is that the result is consistent with the traditional decap design methodology of reducing loop impedance in the PI design. And this is the corresponding PDN self-impedance result with the optimized decap design. Unlike the initial PDN, the provided optimal PDN satisfies the target impedance in the entire frequency range. Finally, we compare the convergence characteristics depending on the size of the action space with the previous work. The upper figure shows the loss convergence of the proposed method depending on the action space size. As you can see, all the cases converged well. And the lower table shows the comparison results with the previous value-based deep Q-running method with CNN value approximator. In the case of the previous work, it only converged when action space n equals 50, but larger cases diverged. Therefore, we validate that the proposed method achieves 4 times larger action space, which lead to 10 to the 45 to 46 order of significant increase in terms of search space coverage. Let me conclude the presentation. In this research, we first proposed a Polish gradient RL-based optimal decap design method using transformer network. The proposed method successfully designed optimized PDN that meets target impedance with the minimum layout area. By direct parameterization of the policy with the transformer network and using Polish gradient algorithm, we achieved 4 times larger action space than previous works. Moreover, the proposed method has superiority on reusability, scalability, and flexibility compared to the previous works based on optimization and genetic algorithm. And we will show the detailed research in the upcoming conferences or journals. Thank you for listening. Thank you.